This video is going to talk about risk aversion, and what we've drawn out here is a utility of money function. So this is a utility of money function, and it turns out this utility of money function is going to exhibit risk aversion. Now, risk aversion means that if a person is risk averse, they would prefer not to take a fair gamble. So if you had a choice between whether you wanted to take a fair gamble or not take a gamble, a person who's risk averse doesn't want to gamble. And by a fair gamble, we mean a gamble, if you want to think about winning or losing money, a gamble where you'd win or lose money where you'd have a zero expected value. And so I've got one of these situations set up here. So suppose somebody's going to start with $30,000 and then they face a coin flip for which they could win or lose $10,000. So you'd have a 0.5 probability of winning $10,000, a 0.5 probability of losing $10,000. That's going to work out to an expected value of 0. So that would be a fair gamble. So would this person want to take a fair gamble or not? This person can be risk averse. And the key thing to see about this utility of money function that I've drawn here is that it's bowed. It's bowed, so it's a positive slope, but it's becoming flatter as we move to the right. Another way to think about it is this is decreasing marginal utility of money. The marginal utility of money is positive, so the slope is positive, but then the marginal utility would be the slope of that curve, and as it becomes flatter, that's showing it's the decreasing marginal utility of money. Another way to think about it is that this curve, if you're familiar with the term from math of a concave function, we're assuming that the utility of money function is concave. So we've drawn it that way. And now what we want to be able to show you that we can see if we've got this shape of a utility of money function, that this person would prefer not to take the gamble. So we're going to imagine that they're going to start with $30,000. If they had the choice to not take the gamble, would they want to take the gamble or would they want to keep $30,000? Since we have a coin flip, it's always nice graphically to use probabilities of 1/2, because then with probabilities of 1/2, if you're going to take the average is just the midpoint. So the average between where the expected value of this gamble is going to be $30,000 because it's a zero expected value coin flip, and you're starting from $30,000. So we can keep the same amounts of money here in terms of gaining $10,000 or losing $10,000. We know that these two distances here are the same, and I've tried to draw them so they would be the same. Now, what I've drawn out on the diagram is that I've listed out here the utilities that the person would get from each of these three different dollar amounts. So this is simple enough. You take, say, $20,000, you read up to the utility of money function, and then project over to the y-axis, and that is then the $20,000 utility of $20,000. $30,000 up to the utility of money function, project over. That gives you the utility of $30,000, and here's the utility of $40,000. Now we want to say, would this person want to take the coin flip or not? If they had the choice, would they want to take the coin flip, or would they want to keep the $30,000? Well, if they keep the $30,000, we know that they'll have a utility of $30,000. They have that for sure. So this is one option they have. Refuse the coin flip, you will be here with this amount of utility. If you take the coin flip, then you're going to get the expected utility. And the expected utility would be 1/2 times the utility you get from $20,000 plus 1/2 times the utility from $40,000. So that's the expected utility. And if you look, we went over a bunch of examples of calculating something like that with on the video showing expected value versus expected utility. So this is what we know it would be. Now graphically, this is why it's nice to have the probabilities of 1/2 here. Graphically, we know that if we come over here to the y-axis, well, because the probability is 1/2, this expected utility is going to be at the midpoint between these two numbers, U20 and then U40,000. You take the midpoint of those two numbers. That's going to be this expected utility. And let me just write this up here. That's the expected utility. Now, the thing we have to say is do we know where to put this on the axis? Well, it turns out the expected utility has to be here. Right? The expected utility, that's exactly that amount there. Why do we know this? Well, this difference here has to be bigger than this difference here. The difference between utility of $40,000 minus the utility of $30,000, that's going to be smaller than this. Why is that? Well, because of what we said in terms of the shape of this utility of money curve. It's becoming flatter. We have the same slope is rise over run. We have the same run in each case. So $10,000 difference in money on the x-axis. Because this utility of money curve is getting flatter, we know that the rise has to be smaller over here than it was for here. Now, this is the rise here, this is the rise here, so this has to be smaller than that. If this is smaller than that, that means that U of $30,000 has to be closer to U of $40,000 than the midpoint. So the midpoint is actually going to be below the utility of $30,000. And there we have it. If you had a choice between not taking the gamble and getting $30,000 for sure, you get this level of utility. If you're going to start with $30,000 and take this coin flip, you get the expected utility. And we've been able to show here that this expected utility has to be below $30,000. And that's giving us exactly what, if you look at the definition of risk aversion, exactly what it says it would be. A person is risk averse if they don't want to take a fair gamble. And here we're able to show graphically that that would be true. Now, there's one thing that they don't have in the book that I have in my notes that on this, and I wanted to show this here to you here. If you take this expected utility number here that you've got from the y-axis and project over to the utility of money function and then down, you're going to get a dollar amount. You get a dollar amount that's associated with this utility of money. That dollar amount has a special term. It's not used in our book, but we can abbreviate it CE, and that's a certainty equivalent. The certainty equivalent of a gamble is the amount of money that would make you indifferent between taking the gamble or having that amount of money for sure. And we've got that by construction here, by taking the expected utility and using the utility money function to go backwards, inverting it and getting this dollar amount. So if we started with CE, go up to the utility money function and over, we'll get exactly the expected utility from this coin flip gamble for $10,000. The certainty equivalent turns out to be important because if that's like the dollar value of this gamble, this is going to be important because the difference between our expected value, the $30,000 that you start with, and the certainty equivalent is going to tell us your willingness to pay for insurance against this type of a loss. So the certainty equivalent is really important because when a person's risk averse, the certainty equivalent will be less than the expected value. And that means that they would benefit from from getting rid of the risk. If this person was facing this risk, they're starting with $30,000, they would be willing to pay any dollar amount up to the difference between $30,000 and the certainty equivalent to get rid of this risk. So in other words, by simply shifting this coin flip for $10,000 onto somebody else, this person we're graphing here would be made better off. and again, if they could get somebody to just take it off their hands for nothing, they'd be made better off by this amount of money here. So there are gains, potentially gains from trade, if this person could find somebody who would be willing to take this coin flip for them. Then this person we've graphed here will be made better off. And in a sense, that's what we end up seeing with insurance. Insurance companies take gambles off people's hands. Say, like, if you're going to wreck your car, well, we'll pay to we'll pay the dollar amount of that loss. So they're in effect taking a risk off of some person's hands, taking a gamble off of somebody's hands, and they're charging you for it. You have to pay a premium, but if that premium is smaller than the difference between the expected value and the certainty equivalent, the person would be made better off, and they would voluntarily choose to buy insurance. So this is a utility of money function illustrating risk aversion, and that's how it is that insurance creates gains for trade in society.